In this video, we're going to be talking about something called an antiderivative and the idea of integration. So first, a function capital F is said to be an antiderivative of little f on an interval I when the derivative of capital F equals little f for all values of x in that interval. So basically, if you take the derivative of big F, you get little f. And so the idea is that this big F is called the antiderivative of our little function f. So if you undid the derivative process, you would get this big F function. So for this first example, we want to find the general solution. This is essentially just asking us to find the antiderivative for this differential equation. So remember, when you're talking about y prime is really just the derivative with respect to x of y, right? This is what y prime is. So we're told that the derivative here is represented by 4x to the third. So if I wanted to find the general solution, that's just my antiderivative. Basically, I'm looking for y, the function y, that I had to take the derivative of to get this. So this is just a power function. So if you recall a power function, if I take the derivative using power function rules, so derivative of x to the n, this was n times x to the n minus 1. So you multiplied your power function by the power, and then you subtracted 1 from the exponent to give you the derivative. So if we take a look at this, we can kind of think of this in a similar way, but we want to go backwards this time. Right, so we know it's going to be a power function. What would our exponent have been in order for it to be 4x to the third? Well, I would have had to multiply by the exponent here, and the number that's multiplying my power function here is a 4. So it's going to be x to the fourth. And then does that work? So y equals x to the fourth. If I were to take the derivative of this, it would be 4 times x to the 4 minus 1, which is 4x to the third. Now, this here is an antiderivative of this differential equation. However, this is not the only possible answer, right? Because there are actually an entire family of functions whose derivative would result in this. And this is where the idea of the general solution comes in. So when you're dealing with antidifferentiation, there is always the possibility of me adding some value. Like I could have added 3 to this, and I'd get the same antiderivative, or derivative, sorry. I could have added 31, and I would have had the same derivative. I could have added negative 31, right? I could have had negative 31, and my derivative would have been the same. So as long as what's being added to this is a constant, we still get this same derivative. So what we do when we're trying to find a general solution is we actually just add a c, and this c represents a constant that is being added. And we call this constant the constant of integration. And we'll see that here in just a minute. So this is a constant. So we're adding on some constant. We know that when we take the derivative of a constant, it's 0, so it would not be represented in this differential equation here. So the operation of finding all solutions of this equation is called antidifferentiation. So that's what we just did in the first example here, or indefinite integration. Now the reason why it's indefinite is because we don't know this value of c. We denote it using this integral sign, so it looks like kind of a skinny stretched s, so that's the integral sign. The general solution is denoted by this. So if you have a function y equals the integral of f of x with respect to x equals capital F of x plus c. So the inside portion of this integral is called the integrand, the function that we're integrating. The variable here, dx, this is our differential, and it's telling us what variable we're integrating with respect to. And then after you've taken the integral, the big capital F here is our antiderivative. It's one antiderivative. It's like the family of antiderivatives because we have to add this constant of integration that we looked at before. So it's not the only value. It depends on what we have in here. So there are a couple properties that we can have for indefinite integrals. So one is called the constant multiple rule. So if you have some function times a constant, so k is any constant, you can basically pull the value of k out and then take the derivative or the antiderivative of f of x and then multiply your antiderivative by k. Very similar to what we have in the derivative rules. So the same can happen here with a negative. In this case, k is just a negative. So if you have a negative function, or if a function works nicely to be factoring a negative out, you can factor it out and just pull it out in front of your integral here. And then the sum and difference property says that if you are taking the sum or difference of functions, and this can extend beyond just two functions. If you're taking the sum or difference of two functions inside the integral, you can basically separate it into two independent integrals of the individual functions, and then you would just take the sum or difference, depending on whatever sign you had here, of those integrals. So just like with the derivative rules, if you had like a string of terms in a polynomial, you can take the derivative of each term individually. Just like if you have a string of terms of a polynomial that you're integrating, you can take the antiderivative of each individual term to give you the overall antiderivative. So let's try a couple examples here. So we want to integrate the following function. So the antiderivative of x to the fourth plus 3. So we want to integrate this. So I know, again, we have a power function. So you're asking yourself, what function would I have to take the derivative of to get x to the fourth? So it's going to be x to some power of 5. Now, if I found the derivative of this would be 5x to the fourth. So in order to get just an x to the fourth, I would have to divide this by 5. And that's actually going to be a general rule for power functions, right? So if you integrate x to the n with respect to x, you're going to get x to the n plus 1 divided by n plus 1. So you basically add 1 to your variable and divide by or add 1 to your exponent and divide by your new exponent here. So it's x to the fifth over 5 plus, so this 3 is a constant. Remember, the derivative of a linear function is a constant. So that would be just x to the first. And that actually still works with the power function, right? Because we could say 3x to the first divided by 1, and that would still give us just our 3x here. And we always need to include our constant of integration because we're not sure how much it's shifted up or down. And that's what this accounts for. Okay. And this would be our solution. This would be our solution. In B, we're taking the integral of 5 times dx. So there's a couple ways we can think about this. We could think of this as a constant times the differential, and you could say, oh, this is equal to 5 times the integral of dx. And when you take the antiderivative of a differential, you just get x. So this would be 5 times x, and then plus c. Or if you were considering 5 to be your function, we could say that we know the integral of a linear function is going to be a constant. So we would still end up with 5x plus c. So either way, we get 5x plus c as our result here. Okay, so this one is maybe a little trickier. We have to really kind of remember our derivative rules in this one. Before I can deal with the secant squared here, I'm actually going to pull this 5 out. I'm going to use that constant multiple rule. So it's going to be 5 times the integral of secant squared x times the derivative of x. So again, we're going to ask ourselves, what function has a derivative of secant squared? So if we think back to all of our derivative rules, what function, when I took its derivative, gave me secant squared? And that's going to be tangent. So this is going to be 5 times the tangent of x. And then again, remember, add your constant of integration. Okay, so for this one, it's a string of polynomials. Remember, we can separate this into integrals, individual integrals like this. So the integral of x cubed, and then you keep your variable of integration with all of these. So it's going to be x cubed dx minus the integral of 4x dx minus the integral of 7 dx. So now that I've kind of set this up for you like this, go ahead and try this part on your own. Try and take the integral take the antiderivative of each of these to get your general solution. So pause the video and then work through it, and we will come back together and talk about this. All right, so now that you've had a chance to work through this, remember that when you're doing the antiderivative of these power functions, you're going to be adding 1 to the exponent and dividing by that new exponent. So this one's going to be x to the 4th over 4. This one is going to be, so it's a 4x to the 1st, so you're adding 1 and dividing. This is a 7, so it's going to be, you could think of this as 7x to the 0, right? Because we know x to the 0 is 1. So you add 1 and divide by 1, so that'll give you your 7x there. Doing a little bit of reducing gives us this here, gives us that there. Okay, so I want you to try this one on your own. Think about trying to make this into a power, and then you can use that power rule that we were just using for antiderivatives. So change this into an exponent, right? Something with an exponent, so it looks like a power function, and then integrate. So again, pause the video, and we can talk about this when you have tried it. All right. So when converting this into something with an exponent, it should be x to the 2/5. Remember, the index is the denominator, and then the power is raised to is the numerator. So you add 1 and divide by that new power. Anytime you divide by a fraction, you multiply by the reciprocal, and that would give you this. And then don't forget your constant of integration. I probably should have a constant of integration in here after taking the antiderivative, but you need to always make sure that it's included in the end of your problem. Okay, so in this one, we have the integral of 1 over 2x. So we actually want to think of this as, we actually want to break this fraction up into a product. So we're going to call this the integral of 1 over 2 times 1 over x times dx. Now the reason why we're going to do this is now I can pull out this 1/2. So it's 1/2 times the integral of 1 over x with respect to x. So now we have to think to ourselves, what function had a derivative of 1 over x? Now, this is not a case where we want to use the power rule, because technically we could write this as x to the -1, right? But if I add 1, that's going to be x to the 0, but then I have to divide by 0, and we're not allowed to divide by 0. So this doesn't work in this situation. So what function had the derivative of 1 over x? Well, if you recall, that was just the natural log of x. So this is going to be 1/2 times the natural log of x. Now, when you're taking the antiderivative of 1 over x, it's not just the natural log of x, it's actually the natural log of the absolute value of x. And that's because we know that the natural log is only defined for values of x that are greater than 0. And in the reciprocal function, 1 over x, you could use negative values if you so chose, right? So to make sure that the function is defined, when we take its antiderivative, we take the absolute value of the denominator here as our argument so that we can have a defined function. And then your constant of integration. Okay. So in this one, we have to do a little bit more algebra manipulation. So what I'm going to do is separate it into a difference of two fractions. So we're going to have x over 2x squared minus 2 over 2x squared. And then we're going to integrate all of this with respect to x. So do a little simplifying. We're going to get x over 2x squared is going to reduce to be 1 over 2x, which we just took the antiderivative of. And then this is going to reduce to be 1 over x squared. And then take the derivative. So I'm going to, I know this one, the integral of 1 over 2x, we just did this. So I'm going to separate this, 1 over 2x dx minus the integral of, and then I'm going to rewrite this one now as x to the -2. Okay, so this one, we just took that derivative in the other example. We took out the 1/2, and it was the integral of 1 over x with respect to x, and then minus the integral of x to the -2 with respect to x. So I know that this is 1/2 times the natural log of the absolute value of x, and then we'll call this plus c, right? So we have to, anytime you take the antiderivative, you have to add a constant of integration, and then we're going to subtract. So remember, we add 1 to the exponent, because this is still a power function. So So it's going to be x to the negative 1. And we divide by our new exponent. So divided by negative 1, then plus c. Now, we have two constants here, so if we want, we could call them c1 and c2. But we'll see what happens with these here in just a minute. So this negative exponent is going to move to the denominator, and then it's being divided by negative, so this is going to turn into positive. And in all of this, we're going to end up with 1/2 times the natural log of the absolute value of x. And then the c1 and the c2 here, c sub 1 and c sub 2, we can actually just combine these to be a single c. We can just call it c when we're done. So we have this plus, I'm going to call this 1 over x, and then I'm going to say plus c, where c is equal to c sub 1 plus c sub 2. We just added the constants of integration from these two to give us our new constant of integration. So this would be our antiderivative here. All right. So we have a couple more examples that we're going to go through, and then we will look at some of the rules. So in this one, what I want to do first is I want to separate this into a sum of two different quotients, and then we're going to have to use some rules here. So this is going to be the sine of x over cosine squared x with respect to x, plus the integral of 1 over cosine squared x with respect to x. Okay, and then this piece here I'm actually going to have to split into a product of two quotients. So it's going to be sine of x over cosine of x times 1 over cosine of x. And you'll see why we do that here in just a minute. And then plus the integral of 1 over cosine squared x with respect to x. Now, a lot of times we want to keep everything in terms of sine and cosine, because a lot of times we have properties that help us here. But in this situation, we want to change what we're looking at. We know sine of x over cosine of x is the tangent of x. And we know 1 over the cosine of x is the secant of x. So we have the derivative, or the integral of tangent of x, secant of x with respect to x. And the integral of, this would be the secant squared x with respect to x. So again, we ask ourselves, which function's derivative would be tangent of x times secant of x? And that's just secant of x. And then plus c, we'll call this c sub 1. And then secant squared x, it's the function whose derivative is secant squared, we saw earlier, is tangent of x. So if we take the antiderivative of secant squared, it's tangent of x. And then we'll call this plus c sub 2. Again, we can put these two pieces here together, c sub 1 and c sub 2, to get our new constant of integration. And we'll call this just c. So it's going to be secant of x plus tangent of x plus c. Okay. So for this problem, I want you to try this one on your own. You have to do a little bit of algebra manipulation in order to be able to successfully integrate this. And give it a try. We'll come back together and talk about it once you have done that. So pause the video, and then we can talk about it once you have given it an attempt. Okay, so the key to this one is really just having to distribute this out, FOIL it all out, and you're going to end up with this difference of squares here. And it's really just using that power rule. So integrate. So you're going to get add 1 to the exponent and divide by that. So you're going to x cubed over 3. And then this is a constant, so the integral of that constant is just going to be 4x. And then don't forget your constant of integration, and you should be all set. Okay, so for this last example, we're asked to find the general solution of capital F prime of x is equal to 9x squared minus x. So basically it's going to ask us to just take the integral of this. And then B is saying find the particular solution that satisfies the initial condition, big F of 2 equals 16. So in this case, they've given us a little bit more information about the function that we're trying to obtain. And we are told that the function, the new function that we're going to find, at x equals 2, it's defined to be 16. So we can actually use this information to get rid of our constant of integration. So we'll see that here in this example. So let's look at part A. So part A is finding the general solution. So we're going to take the antiderivative of big F prime of x with respect to x, which is the antiderivative of 9x squared minus x. Right, so we're integrating this, and that's going to be, so add 1 to the exponent, so that's 9x to the third, and divide by the exponent, minus x squared over 2, and then plus c. So this is our general solution, f of x. So this is the general solution, which is the integral of big F prime. Now, if we want to find the particular solution, like it asked us to do for part B, we want to evaluate f at 2. We know that it should equal 16, so we can set it equal to 16 to try and calculate the value of c. So we know f of 2 is equal to 16. So that tells me that. This can reduce, by the way, to be 3x cubed minus x squared over 2 plus c is what f of x is equal to. So it's going to be 3 times 2 cubed minus 2 squared over 2 plus c is equal to 16. So that's going to be 8 times 3, so 24 minus 4 divided by 2 is 2, plus c is equal to 16. So that's 22 plus c is equal to 16. So then c is equal to 16 minus 22, which is negative 6. So our particular solution then was going to be f of x equals 3x cubed minus x squared over 2 minus 6. So this right here is our particular solution that satisfies the initial condition that big F of 2 is equal to 16. Okay, so for this next part, you need to go into your textbook, take a look at page 282, and fill out that chart that you have in your notes. These are the basic integration formulas that you need to know. Most of them are pretty intuitive because they're just kind of like the reverse process of finding the derivative, but these do need to be memorized. You have to know all of these. So go ahead and into your textbook on page 282 and complete that chart so that you have that to refer to.